All right, guys, so back for part 2 of our study of the calculating the enthalpies of reaction or heat of reaction. And on the last video, we stopped on this slide, and we were at the end we were talking about this particular reaction. And in just a few minutes, we're going to use this as our reaction that we calculate the heat of reaction for. But before we do, a couple of things I want to point out. In a formula, when you see this funny look like a backwards 3. This is a Greek letter. It's called a sigma. And so when you see this in a formula, it means to sum up what comes after it. So we're going to be adding up the bond enthalpies of the bonds broken, take into account the moles that we have of them. And then we're going to sum up the bond enthalpies of the bonds that are formed as the products form. And then again, considering how many moles we have of each bond. And then we're going to subtract. Also, if you look at this diagram, I want to remind you of the enthalpy diagram that we normally see, what it looks like usually. This is a little different version, but you normally, like for this one, I'm going to use this one for an example. This represents the energy of your reactant. So this would represent here what you see in this. So you have your methane plus your diatomic chlorine. Well, for any reaction to occur, these molecules have to collide with sufficient energy to reach what we call the activation energy, which in this case is up at the top point here. So on the energy diagram, we normally see it written like this, shown like this, and then you would see the products kind of level off here in the end. This represents the energy of your products, which is what we see here once the products have formed. So this energy difference from where the reactants are to the top of this hill is referred to as your energy of activation, or E sub A. Up here at the top, this is where you have what we call the activated complex. And if you look in this part here, you'll see that one of the hydrogens has kind of pulled away or broken off. It had to be broken of the C carbon here. And then the chlorine has been dissociated. Notice it's broken apart. They're no longer connected. So this is your activated complex. Once the reactants have reached sufficient energy to break these bonds, then they're ready to form products. So you'll notice the energy lowers until eventually it levels off. So the difference between the reactant and the product here, this is your overall energy change. And notice the energy was lowered, products were lower energy, so this is exothermic. So it will be given a negative delta H, which is typically exothermic processes are thermodynamically favorable. All right, so here's the formula. Let's take a look at these particular molecules that we saw in the last slide. What you want to do is you want to consider the Lewis structure. So I'm going to sketch this out. So with the methane, if you draw his Lewis structure, this is what you have. Carbon, hydrogen, single bonds all the way around. And with chlorine, if you draw his Lewis structure, it's diatomic, Cl-Cl, there's a single bond. Of course, when you put all your electrons out, this is what it looks like. So, as they begin to come back together, what's going to form is the CH3Cl, and the Lewis structure for that is going to look like this. 3 hydrogen single bonds coming off of your carbon, and a chlorine off of it, and of course your lone pairs would be here. And then the HCl is going to look like this. All right. So what we have to do is we have to break all of these bonds. So I'm going to write this formula. It's going to be a little more simple looking than this, but you'll get the idea. So the heat of reaction, or the overall enthalpy change in the reaction. Okay. Remember, we do the bonds that are broken first. So the bonds that are broken are the reactants. So what I have to do is I have to break 1, 2, 3, 4 of the carbon to chlorine single bond. So I'm going to say 4 moles times, and I'm going to write this first of all without putting any numbers in, carbon to chlorine single bond. I'm sorry, carbon to hydrogen single bond. I don't know why I said chlorine. So carbon, hydrogen single bonds. 1, 2, 3, 4. And now I got to break this bond. Break it. So I got to break 1 mole, there's 1 of them, of the chlorine-chlorine single bond. So Cl-Cl. Okay, so those are the bonds that are broken. Okay, remember the formula has the negative here. So now we're going to take the bond enthalpies of the ones formed. So you're going to come over here and you're going to account for the bonds that have to form. So we have to make 1, 2, 3, so that's 3 moles of carbon, hydrogen, single bonds. And don't forget this one. This is the new bond that formed. We're going to make 1 mole of the carbon-chlorine single bond, so CCl. And then finally we have to form the HCl, so plus 1 mole, I'm running out of room, got to break that, HCl. Okay, now look to the bond energy diagram that was on the previous slide. It was in your notes. And so what you're going to do is you're going to look up these values. Now we're going to substitute those in. So notice also in the bond energy values, if you look at the units, those are in units of kilojoules per mole. So that's important to recognize. So here's your mole here, it's going to cancel. So I'm going to plug in 4 moles. And now for the carbon to hydrogen single bond, it's going to take 413, so look that up on your chart, 413 kilojoules per mole of energy to break, to break that bond. Plus, I got 1 mole of the chlorine-chlorine single bond. If you look that up on your chart, that's going to take 242 kilojoules per mole of energy to break. Okay, so those are all the bonds broken. Now do the same thing for the bonds that are formed. 3 mole times the CH. There were 3 of those, so that was 413 again, kilojoules per mole, plus 1 mole of the CCl, which was 328 kilojoules per mole. And then finally, 1 mole times 431 kilojoules per mole. All right, kind of run out of room on that one. Now notice though, the moles cancel here, the moles cancel here, the moles cancel here, the moles cancel here, and the moles cancel here. So the final value and the point of why I wrote all that in, because you don't have to write it in every time, but your final unit is going to be kilojoules of energy. Okay? So when you add all this together, here you're going to end up getting 1894 kilojoules. I'm breaking this all apart, y'all. When you add all these together, you get 1998 kilojoules. So when you now subtract, you're going to end up getting a negative 104 kilojoules of energy. So this is the enthalpy of the reaction. So 104 kilojoules of energy are released. The negative signs means it's exothermic, so that means the energy was released. And from the previous slide, you remember that there was a net release of energy. We'll look at one more. So here, I'm going to real quickly sketch this out. Hopefully the video will not cut me off. F, F. And if you draw your Lewis structures, make sure you put out all of your electrons just to make sure you have truly single bonds here. This is balanced 1, 1, 2. So pay attention to that. So this is going to form 2 HF. So I'm going to write it out expanded. There's 2 of them formed, and that's important to understand here, y'all. Okay. So now, delta H of the reaction is going to be equal to 1, I'm not going to put the mole unit, but there's 1 mole of HH. I'll say 1 times the bond dissociation energy of the HH single bond plus 1, there's one of those, times the